Hey guys, welcome back. So by now we've finished the regression quiz and we know the basics of regression, how to calculate a linear regression. So now we're just going to look into it a little bit deeper and find some smaller minute points and look at just some general regression wisdom. So that's the name of this chapter, chapter 8, regression wisdom. So in the words of Yoda, we want to use wisdom with regression, you must. I know, that was terrible. I'll stick with my other equally terrible accents. All right, so the first piece of wisdom that Yoda would give you is that you should always graph the residuals. So never just run well, first of all, always graph the scatter plot itself to see if you notice anything unusual, but never just run a linear regression and call it good because you have a high a coefficient of determination. That's like the worst thing you could do. And then on top of that, always graph the residuals. And remember, when we're graphing residuals, we're looking for patterns. So here we have, this is for the dive heart rate for penguins. So what is their heart rate as they're diving for the duration of their dive? So I guess some of them could dive for several minutes. That's very impressive to hold a breath that long. Anyway, but you notice that their dive heart rate, in order for them to be able to stay submerged for so long, they had to have a really low dive heart rate. If they had a higher dive heart rate, then the penguins would surface much quicker because they were using up all the oxygen. Their oxygen saturation wasn't very good in their blood. So anyway, kind of cool how those two are related to each other. It kind of looks linear, and in fact, you could make a linear model if you just look at the scatter plot itself. But whenever you graph the residuals, and now that we'll know, well, there's kind of a gap there and on the bottom here, and if we look at graphing out the residuals, there's a gap here and a gap on the bottom as well. So it shows us that the data itself is actually really curved, like you see here, and it's not necessarily appropriate for us to use a linear model. So what do? Well, after this chapter, chapter 9, we're going to talk about re-expressing data, which is pretty stinking cool. And if you look, this actually kind of looks like a 1 over x, so like a reciprocal graph or something like that. And so the way that we could fix it would actually be possibly by squaring the dive heart rate. So if we take the dive heart rate and we square it, so if you remember squaring it, if it's 1, it doesn't change anything. If it's less than 1, and it has this kind of it'll make it smaller, right? But if it's greater than 1, then it's going to increase it, and the further we get away from 1, the more of an effect it's going to have on it, right? So if we square 4, that's going to be 16. If we square 10, that's going to be 100. So it's going to have a much larger effect the further away it is. So what's going to happen is these values that are less than 1 or really close to 1, they're going to actually be kind of smaller, and then the values that are higher than 1, the further we get away, the further they're going to get moved up. So what's going to happen is these values are going to be moved down, these values are going to be moved up, and it actually should straighten out the scatter plot. So instead of writing a linear model where the predicted dive heart rate is some slope times minutes, our explanatory variable, plus some y-intercept, now we're actually going to square the dive heart rate. So some dive heart rate squared with the re-expressed data. We'll have a new slope, a new linear regression, a new y-intercept, but it'll actually increase the accuracy of the model, remove more variation out of it, which is going to be really, really cool. And more importantly, it'll actually be appropriate to use a linear model because we re-express the data to make it straight, okay? All right, so the next thing is that if we look at the duration minutes and we look at those residuals, we can actually take all these residuals and kind of, if I move this across here, kind of like a net, and I just and I picked up all those points, or another way of looking at this, if I take all of the residuals and I collapse them kind of like in a marginal distribution, so I don't care the duration, the minutes for the prediction, I just want to know all those residuals and collapse them across to this marginal distribution, it would fill in more likely a bell curve, and then from that we could get the standard deviation of the residuals themselves, and then anyway, we could get a standard deviation of the residuals, and that would tell us the average prediction error. So what is so standard deviation is like what we would expect it, like a typical or an average, an average deviation from the mean, right? So the standard deviation of the error, which we use the E for error because we can't do R for residual because R has already been used as a parameter for the correlation coefficient. So we have S sub E, which is the standard deviation of the error, which is going to be the average prediction error, which is on average, how much could we expect, how far do we expect our predictions to be from the actual true values, which is essentially what's going on here. All right, so how is that calculated? Well, the standard deviation, if you remember, was calculated with observations minus the average squared. So the deviation squared, sum of the deviation squared divided by n minus 1, and that'll give you the variation. So then we take the square root of it to get back to the standard units of whatever units we're using for our y variable in this case. Now the standard deviation of the error is very similar because the error is the observation minus the mean, or sorry, the error is the actual minus the predicted, and the actual value is our observation, and the mean is going to be the model, which is what was predicted. And that's always going to add up to 0. If we take the sum of all the residuals, it's always 0. So it's really the same thing. So our deviation is the error. That's how far it was from the model, right? So the deviation of the error squared, sum of that, but then we're subtracting by n minus, or dividing by n minus 2. That's because we're estimating 2 parameters instead of 1 parameter. If that kind of is a little fuzzy for you, don't worry about it. It messes with a lot of people's heads. And the larger our sample is, the less that difference matters in the first place. So don't worry about it too much. Then down here, I did want to go into this a little bit. So the correlation coefficient, correlation coefficient squared, which is going to be r squared, is going to be the coefficient of determination, which tells us the percent or the proportion of variation in the y variable, that, or the response variable, that can be accounted for, that can be removed or accounted for by the model. So if we take our 1 minus the r squared, that's the amount of variation we have remaining, or the proportion of the variation that's remaining. So if we take our standard deviation of the error, so the S of E, the standard deviation of the error, and we square it again, that'll get us back to the variation, which is the total amount of variation we have in the residuals. And if we take the variation that's remaining in the residuals, which is from the how far off our data was from the actual model, right? Because the models are, no model is going to be perfect. They're all going to have error in them. And then we're going to divide that by the variation, the total amount of variation we had in the y variable, which is just if we would have guessed x across, or average y across the board for everything without using a model. This is going to tell us the proportion that's of variation that's remaining in our residuals. Now, if we do just the r squared, that's going to be the total variation we had minus the variation that was remaining from after our model, the standard deviation of the error, basically the residuals. Standard deviation of the residual squared, okay, the variation that's remaining in the model divided by the total variation we had to start out with. So that's going to be the r squared. I just thought that would be nice for you guys to know. All right, so if we graph our residuals out instead of, the bell curve I was talking about here, but if we graphed it out as a histogram, then you notice there's going to be some kind of clumps on the ends here, and that actually comes from, so I guess we're looking at predicted value of calories for cereal, predicting calories in cereal from the sugar. Okay, so the predicted amount of calories that we would expect, and then here's the actual amount. So these were much more calories than we would expect from the amount of sugar, and these were much less calories than what we'd expect from the amount of sugar. So the reason for that is we have different groups. So these outliers we kind of see here, if we sift through the residuals, you might see patterns. So the patterns you see up here, these might be like granola. So they had a lot more calories than what we'd expect, we would predict from the amount of sugar, because the calories were coming from the fat content in the granola, the healthy fat or whatever, instead of from the sugar itself. But down here, they would have far less than what we would expect in calories, because those are some different kind of cereal. I don't know. And then all the other cereal is the cereal that's in the middle. So when we notice there's groups, we can look through and go back at how we gather the data and what those points actually were to see if we can notice some pattern, and maybe we have subgroups. And so here we have subsets. So all the data must come from the same group. And here are the 3 different types of cereal that they had. They have bottom shelf, middle shelf, and top shelf. I did that backwards. But you got the green, the fuchsia, and the blue. And you see, if we broke those into 3 separate groups, we would have 3 different models with one of them, the top shelf, the healthier cereal, would be very different than what we would expect from the rest of them. So anyway, if we can break it down into separate groups, then that's what you should do, because it gives you better models, and you can move more variation by just specifying this is the model that we have for top shelf, middle shelf, and bottom shelf cereal. Of course, because we have cereal that's geared towards adults, which are on the top shelf, which is eye level for them, and the cereal that's for the children, the kind that I like, the good kind, which is down on the bottom shelf because it's eye level for the kids. We saw something similar with this with the NFL weight distribution. So depending on their position, we would expect very different builds and weights. Let's say that we want to make a model to predict the weight of a football player based on their height. Well, we would get very different information. Say they're all around 6 foot tall, and then there's going to be variation in that as well. But we get very different information from the model if you had a 6 foot tall lineman, or if you had a 6 foot tall wide receiver or kicker, right? Linemen get hit all the time, where a kicker, it's a penalty if you touch them at all. So you don't have to worry about that. So they're going to have very different builds, right? So the smart thing to do, instead of making one big model in general, which would have a ton of variation because there's a ton of variation in the weights here, what we should do is break it down into subgroups, and we can make a group for maybe linemen and a group for the kickers could have their own separate group or whatever, and those models would be much more accurate, kind of like what we could see with subsets here with the serial. All right, so the next thing we want to discuss is that the further we get away from the mean, the less that we should trust the prediction. So our safest estimate is always the mean point. And remember, the mean point, every model, regardless of what slope you would have and the strength of the correlation, will always go through the mean point, which is when we have average protein and average fat content. Okay, now the strength of the correlation allows us to deviate with the change in our the further we get away from the average protein allows us to change how far we were able to get away from the average fat content, right? And that's the scale factor we use there is the correlation coefficient, okay? All right, so the further we get away from average protein, the less we should trust the model, because the model is going to be kind of a more conservative estimate if we would just guess average fat content across the board. That would be the most conservative estimate for that, okay? But so the further we get away from it doesn't mean necessarily that it's actually going to be a problem. Like if we did an protein content for 40, it's probably going to be pretty good, but we would trust the estimate a whole lot more if it was closer to the mean point. So in general, the further we get away from the mean for the explanatory variable, the less we should trust the prediction. Our extrapolation warning. So we cannot predict the future. We can really only interpret our model or our graph from the domain that we are given. So the range of x values. And so if no one can predict the future, right? No one knows what's going to happen in the future. We don't know if current trends will continue. And so the problem is that in stats, we know this to be true, right? No one knows the future, right? But people still get paid millions of dollars to try to predict the future, to try to tell companies what to expect with the market and stuff like that, right? And so like for instance, a good example is the fact that we were told there were going to be 2 million people that died from COVID, and it's about 10% of that, right? So way off, right? But still, it was extrapolating. We were estimating what was going to happen in the future. No one really knew what was going to happen, et cetera, et cetera. So all the time people are paid to make predictions, even though we know from statistics that you cannot extrapolate. No one can predict the future. So there you go. We don't know if current trends will continue. We don't know. There's so much like volatility in the market. We don't know. And if it's going up, then it could go down, or it can continue to go up. You just simply don't know. In the long run, we might know that long run behavior would approach the empirical probability, which we'll get into that. But in the short term behavior, we don't know what happens. We don't know what's going to happen in the next 5 years. Okay. So in 1970, oil cost about $17 a barrel, and $2005. About what it had cost for about 20 years or so. So it was pretty stable for a long time. Then within just a few years, the price surged more than doubled to $40 a barrel. In 1975, a survey of the top 15 economic forecasting models, again, people paid lots of money trying to predict the future, even though they know that it's not going to happen. Built by economists that include Nobel Prize winning economists, found predictions for 1985 oil prices that range from anywhere from $300 to $700 a barrel. So going from 1973 to 1974, it increased pretty drastically. From that, they made a model which had an average slope anywhere from $30 to $70 per year, that it was increasing over the next 10 years is what they were guessing. And so what ended up actually happening is, yes, it did continue to go up, which again, no one would have known that or could have known that, but it didn't go up as drastically as they thought they did. So if we are going to make a prediction, you definitely should not make a prediction between just 2 years or short-term behavior, because we can have a lot of volatility, and the likelihood that trend continues is even less likely. So the more data that we use, more of a conservative or better estimate that you would get if you're reaching back even further. Okay, so the same thing, like, and we will of course talk about climate change because we talk about all the controversial stuff. But if we only look at 1 year to another year and there was a big difference between that, it'd be much better and have much more accurate predictions for total climate change if we went further back than if we just looked at 2 years. Okay, similar idea going on here, right? All right, so the actual amount that it went up for the next like 5 years was an average of $7 per year per barrel. Okay, for a barrel of oil instead of the 30 to the 70. So they were way off. And if their model was correct, then for 1985, it would have been way up off the graph. And this is 80, so it'd be more than 9 times that, way off the page. Okay, you get the idea. It's going to be terrible. Or that's what they were predicting, and people freaked out, of course. All right, but what actually ended up happening? Well, it actually went back down. And so when would it go back down? We don't really know. It could have been bad for another 10 years, 20 years, but eventually it went back down. So again, kind of in general, long-term behavior, things kind of tend to average out. Okay, so don't freak out. So then the next thing is then in 1998 and 1999, there were 2 more companies or whatever that came out with 2 more models for what they thought were going to happen with the oil prices. So there was an increase around that time, or they thought it would go back up. One of them thought it would go up faster than the other one, but anyway, just 2 models. They were paid to do it, so they did it, and that's what happens, even though no one should trust it. All right, so then the next thing is that if we look at what actually happened, they were way off. So no one was, again, like here, we couldn't predict like when it would go back down, or if it would even go back down. Of course, probably it would. Same thing, no one knew that the oil prices were going to go up again. Of course, they went up around this time. This was 9/11, so in Kuwait, and all the oil issues that was going on with Iraq. And yes, and so prices of oil went way up because of the conflict in the Middle East, and probably because of shipping and issues like that. And so prices went up. And could anyone predict that volatility was going to go on? Probably not, unless you were involved in the plot in 9/11. I don't know. So, all right, another thing we need to look at is large residuals. So if we have a large residual, like this point up here, it's clearly an outlier, right? But another way of looking at it is that it's got a large residual. It had an actual value that was really far off from what was predicted. Well, this one value here can change the actual slope, okay? And another thing, so if we did not have this orange point here, instead of this orange line of best fit, we'd have the blue one. Well, which one is a better model, the orange one or the blue one? Well, if you look at it, it looks like the blue one clearly fits the data much better. So if we could, we would remove this point here. We make sure that we're very clear about what we're doing. We can't just remove points, but as long as we tell them what we're doing and why we're doing it, if it gives us a better model, we can. So let's say this was, this is kind of fun. Oh, sorry, today's so political. But anyway, so we have votes for Nader and votes for Buchanan. So these were 2 Democrat and Republican, I think, in Florida in 2000. So they did a new ballot called a butterfly ballot, which I think instead of having like all of the Republicans on the left and Democrats on the right or something, they switched them for like whoever the primary candidates were, and then they switched it for the rest of the party. So people, as they were checking the boxes, they were voting one party essentially, and then they checked the wrong box at the end because they switched them. And anyway, it ended up causing a lot of confusion, and old people know about it, but I was too young. I was 7 years old in 2000, so I didn't remember this being an issue. But anyway, they're called butterfly ballots, and you can look it up if you want. So the number of votes that they had for Buchanan were far off from what would have been predicted based on the votes for Nader as well. So this slope that we could do here. Anyway, if we remove that point as an outlier, we would get a much better model, and so that's what we'll do. We'll just make sure that we tell people about it. Then we have something called high leverage points. So the further we get away from the average value of X, so this is like a shoe size and then IQ. Clearly we know if we just looked at this data over here, there's no relationship, there's no association between shoe size and IQ, right? That's kind of silly. Speaking of silly, so is Bozo the Clown. So Bozo the Clown had some really large shoes. Those are his shoes. He's kind of known for it. And so he would be what we consider a high leverage point. So because his shoe size was so far from the average typical shoe size, because clearly that's not how big his feet are, it's just his shoes are goofy, then that would mean that he would have high leverage. So if Bozo was a bozo, and he was not very intelligent, then instead of having a slope of 0 or a correlation of 0, we would actually have a negative correlation because this one point had such large z-scores. So if it had, like, let's say he was positive 10 and then -4 for IQ or something like that. Okay, so if he was an absolute bozo with really large feet, that one product of the z-scores would be really negative, and these would probably balance out to 0, but this one value here would be negative and would make it seem that we had a negative association altogether. Now, if he was really, really smart, so again, 10 standard deviations above the mean for shoe size, and then let's say 4, even just a positive 4. Now, the sum of the products of the z-score would be equal to 40, and that positive 40, even though these would all kind of cancel each other out, right? The positive and the negative ones, and the positive ones would all pretty much cancel each other out. But this one positive way up here would cause us to think that there was a strong, maybe even a strong positive correlation between shoe size and IQ. And so we just got to be really careful. Anytime we have a X value that's so far away from the mean, it has high leverage. So it might be influential, it might not be influential, but it definitely does have high leverage. It does, if it follows the trends or not, then it would be influential. But anyway, it definitely has high leverage, and we need to be very careful with those. All right, so talking about influence. So influence, just points that have a mean that's far away from, or sorry, an X value is far away from the mean, they have leverage. They have the potential to have influence. Whether they are influential or not, that depends on if it follows the rest of the trend. So if we just look at the blue dots here, clearly that would be positive, right? And it looks like there's a moderately strong association. Now, if we added the purple dot to it, the purple dot's not actually going to change it's not going to change the slope much at all, because it follows along the slope, but it is going to change the correlation coefficient, because this value is going to be such a large z-score. So this might be, I don't know, 4 and 4. So the sum of the products of the z-scores would be like 16, which is really unusual. And that's going to give us a lot stronger, a lot higher correlation coefficient than what we would typically have if we didn't, which would be this part here that's in the 0.7. Okay, so without that point, it'd be 0.7 for the correlation coefficient. With it, it would be much higher because of the large product of the z-scores. Does not change the slope, but it does drastically increase the correlation coefficient. All right, what if we added this green point instead of the purple point here? So the green point, if we did that, we would have a slope. Oh, I don't think, yeah. So anyway, the purple one wouldn't change the slope very much, but the green one, it would change the slope quite a bit. So instead of a positive correlation, this one would lessen the value, or maybe actually it wouldn't. I have to think about it. But if it was, and because it still looks like it's a positive and a positive in the right quadrant, so, but it would actually change the mean point. I have to think about this one. But if it lowered the point, kind of drew it towards it, which is how conventional wisdom would think, then it would actually change the, it would draw it towards it, which actually kind of makes sense. So it would change it, and it would lower the correlation coefficient as well. It wouldn't, or maybe it would raise it. I don't know. I have to think about that one as well. Depends on the actual like specific points, but it would have influence because it would change the actual slope, because it didn't go along with what the original one would have been. That's kind of the main point you need to take away from it. All right, so the difference between outliers, leverage, and influence. So an outlier has a large residual like we have here. What effect do outliers have on it? Well, they can change the slopes themselves, but the real issue is that if we remove the outlier, then we would have a much better model. And the red model here with the outlier is not that far off, but why would we use a model we know isn't as good as it could be if we could just remove one point, tell everyone we're doing it, of course, be forthright about it, and have a better model. All right, then here we have this point and this point. Now, both of them have leverage because they are so far away from the average value we'd have for X, but the only one that had influence was this one here, because it actually changed the slope. So this one would drastically lower the slope. Instead of a positive correlation, now we thought we had a negative one because this one was so far off. We're over here, excuse me, it does have leverage because it is so far from the average of the X, but did not change the slope, or not a significant change in the slope. So we wouldn't say that it was very influential. It would give us a much higher correlation coefficient though as well. All right, so let's look through this. I'm trying to make sure the video doesn't go too long. But anyway, anytime we're starting a new chapter, the videos are always going to be a little bit longer because there's a lot of new stuff that I'm going to throw at you. And clearly, the second day that we do this will be a lot shorter. So our table on the right shows the number of seniors who graduated from a small college during the latter half of the last century. The data is not available for all the years, especially those longer ago. So make a scatter plot and describe the trends you see in the direction. So you don't actually have to make a scatter plot because I did it for you. So yeah, I did do it for you. So on this one, notice the general trends. It went up and then it went down, then it went back up. So again, no one could have predicted that, but now that we know that that's what happened, we can actually make models off of it. So the first part is that they said in 1969 there was no there's no data to show the graduating size or the size of the graduating class of 1969. Create an appropriate model and use it to estimate the size of that class. So 1969 was about right here. Okay, so just looking at it, we're predicting something around 440, 450 or something like that. But what data would we use in order to make that model? Well, if we use all of the data, knowing there's separate trends here, this is kind of like subgroups, right? So it's kind of like the top shelf, the middle shelf, and the bottom shelf, right? We want to find the appropriate subgroup for it, then use a model with that subgroup data. Now, if we use the overall model for all the data that we have, then the model will look something along the lines of this. Now, does this model ever really fit any of the data? No, because it didn't fit that data, and then went up, and then went down, then went back up. So this overall, even though we're using more data, you think more accurate? No, if there's subgroups, we need to use the appropriate subgroup. So what I'm going to do is I'm going to use the data from 0, which is 1950, all the way, I think, to this value. I think it's going to be where I cut it off, which is going to be 26 years after, or 1976, which is that value there. So that's going to be my model that I'm going to create, which is going to look something along the lines of that. Then I'll use that model to make a prediction for 1969, which would be much more accurate than the model, the data I would get from the model if I use the overall trends. So to put this in the calculator, just go to Stat and then Edit. And for list 1, they actually do this quite a bit, and it's kind of nice. You'll get used to it, but we're doing years since 1950. So for the X value, we're going to do 0, 3, 7. I already calculated for you, which is pretty nice. And then the years graduate. So we're not actually going to use this, and it's going to be years since 1950 instead of the actual year itself. All right, so the first thing we want to do, you can graph out, you can graph out the scatter plot if you're interested. So plot 1 and plot 2, or list 1, list 2, and then hit zoom 9. And that's going to graph that out. Okay, so that's going to be our data all the way up to 1976, I believe. And then we want to create a linear regression. So we're going to go to Stat, arrow to the right, Calculate, Linear Regression, which is the 4th option. I'm going from list 1 to list 2. I do want to store the regression equation because I'm going to use it to evaluate the 1969. And store the regression equation as y1. So we'll go to Variables, Y Variables function, y1, then hit Calculate. So here we have our model, so our slope, our y-intercept, and then the coefficient of determination tells us that 95.6%, for rounding, of the variation in the class size can be accounted for by the model with the years since 1950. And then the correlation coefficient, of course, is the sum of the product of the z-scores. This shows that if it is actually linear, and we checked it was linear, right? So this is an appropriate summary for the strength of the correlation. So the correlation, it's a positive, the association is a positive, a very strong positive correlation between years since 1950 and the class size. All right, so the next thing we want to do now that we have our model is we want to, I guess you could hit graph if you want. So graph, and that'll actually graph the model. It automatically turns it on after it's stored it in Y1, which is kind of cool. So you can see that. You can hit trace if you want, and then arrow up, and you could go over to, if we're doing 1969, that's going to be 19 years. So our X value is going to be 19. And you can get an estimate from that, but the best way to do it is just to evaluate it. So we're estimating about 468, which is, okay, about what we were thinking. Anyway, so to evaluate it, we're going to quit out of that and go to Y variables function, Y1, hit our parentheses to evaluate, and I'm going to evaluate 19 years, and that'll give me the exact value. So that would be our prediction, which is a lot closer than if we would have used the other model, or used all the data to make that model. Okay, so that is it. I hope you enjoyed, and right under 30 minutes. So I'll see you guys tomorrow. Have a good day.